Susan has taught you all about stoichiometry. She's taught you about dimensional analysis and probably about finding limited reactants. Yes? Okay, you're good to go. So now we're just introducing one new variable into the equation, and that is the concept of energy. In this case, there's a negative amount of energy, which means this reaction is losing energy. Now, for those of you in biochem last year or in chemistry, you remember that that means it's an exothermic reaction, which means you're losing energy. So energy's on the Y here. This much is this number right here. So every time 1 mole of oxygen reacts with 2 moles of hydrogen, they release, upon formation of 2 moles of water in the gas state, that many kilojoules of energy. And that's what mole of reaction means. It means as it's written, that's what you get. So again, that's for every 2 moles of hydrogen and every 1 mole of oxygen. So let's do a little math around this. Based on the equation above, answer the following questions. How many kilojoules are released when 1 mole of hydrogen is combusted? You can do this in your head because this says for every mole of reaction you get that many, but every mole of reaction involves 2 moles of hydrogen. So if you only combust 1 mole, you get half as much. But let's do it formally now. So the way we do that is using dimensional analysis that Ms. Kaufman taught you. So let's start with what we know. We know that ratio, so we're going to start with that. You can also start with this number. It just doesn't matter. Those are 2 pieces of information you know. It doesn't matter what the starting point is. But I'm going to start with that ratio because it sort of just makes a little bit more sense logically. So it's that many kilojoules per mole of reaction. Now I just said that there's a 2-to-1 ratio, but let's formally write it out. For every 1 mole of reaction, you have 2 moles of hydrogen. And we have to keep going because we want to cancel everything out but kilojoules. So now we need to get rid of moles of hydrogen. So we're going to times it by the fact that we are only combusting 1 mole of hydrogen. La la. And you're going to get basically half of that, like we discussed, which is negative 285.8. Now this is the same as was in your packet. So it's the same exact problem. But now we're going to switch the numbers up a little bit. Okay, what if we aren't given something as simple as 1 mole? What if we're given, like, say, grams, which is a lot more reasonable? You don't measure moles in the lab, you measure grams. So this time, let's start with this is our known quantity. And all we're going to do is use a little dimensional analysis to jam through, you know, the answer. But we don't know the ratio of grams of hydrogen to energy. We only know the ratio of moles of reaction and therefore moles of hydrogen to kilojoules. So we got to convert grams to moles, and that's not a problem. So we look up on the periodic table and get the molar mass is 2.02 grams per 1 mole, and get to cancel that out. Now we can keep going. Let's see. There's every 2 moles of hydrogen for every 1 mole of reaction. Now we use our final unit up here, negative 571.6 kilojoules per mole reaction. And just take a look for a moment at the units. Notice what all cancels. What you're left with is the kilojoules. And when you get this thing out, you take that, whoops, this number times that, and times that, divided by this and divided by that. Okay, so you get, if I have done this correctly, 21,200 kilojoules of energy out. Might want to pause and make sure that you can do this calculation as well. Okay, next is how many grams of oxygen are required to produce 2,500 kilojoules? So let's start with what we know. We want to make 2,500 kilojoules. Well, we know that if we burn up 2 moles of hydrogen, we're going to make that many, and 1 mole of oxygen, and we're going to make that many. Okay? But what if we want to make more? 2,500. That's fine. Then we can use the same ratio that we've been using and work through the problem. So let's start with the ratio we know, which is that one up there. This time we're going to put the kilojoules on the bottom because we want to actually find the quantity of oxygen, which is going to go on top ultimately. And that's per 1 mole reaction. 1 mole reaction. And then finally we get the grams per mole. Okay? And then you go through this times that times that times that, divided by the bottom numbers, and you get about 140.0 grams of O2.